Hey guys, we're going to do lesson 10.1, which kind of in the curriculum, but we're going to do it like an abbreviated version. It won't take too long. But it's on linear programming. It's kind of a review of lines and things like that. Although it sounds complicated, it's really not too bad. Typical problems that they solve is kind of like this one. You have a recipe with all these different ingredients, um, for these two different batches of cookies. The question is, if you have all of this stuff readily available, how can you maximize the amount of food, right? And all these questions deal with maximums and minimums with a whole bunch of stuff going on. And they add another variable to it. So it seems complicated, but if we break each part down into lines, we can kind of solve these questions and it's not too bad. I would ask if you're on your laptops that you guys open up Desmos. Even if you're on like an iPad, you can still open up Desmos. We're going to do this lesson in Desmos. Usually I do it with the TI 84 calculator, but Desmos is going to be so much quicker and easier for you guys to do it. So um, we'll do that. Okay, so we're going to get into the non-word problems today. Again, Desmos is fine instead of the graphing calculators. But here's like a typical question, right? We're going to introduce this new variable z, which is going to determine maximums and minimums. We also can call it f of x comma y, because we're basically plugging in x and y versus just like f of x, where you just plug in x. Not sure what's going on there. But we're just going to plug in both, and then that's why we call it f of x comma y. That's going to actually be the final step. What happens before that is that we're actually looking at a series of constraints, right? So these are what's going to determine the values of x and y that I can now plug into the z equation. So these constraints are going to give me a part of the graph where like x's and y's work for all three graphs, right? So normally if it's a graphing calculator, you want to get all of these solved for y and just be careful. Like in this one, it's going to be a negative y when you subtract 3x. So then you divide or multiply by -1, the sign's going to flip. Same thing here, the sign would flip if you do that. If you do it on Desmos, though, you can just type it in exactly like you see it. So we can do that, right? And then what it looks like on Desmos is going to be this. So I already did this one out, I believe. Oh, no, I haven't. That's a new one. But you can do it on Desmos. This one's going to be at the bottom here. So once you've plotted them, you kind of see that these are the lines, and then with the inequalities, right? This one's going to be y is less than or equal to, right? So you can kind of see that one would be this one over here. So less than or equal to, if you're ever unsure of how to shade it, if it's less than, it's going to include negative infinity on the y's. So like, okay, I'm going to shade below this part because that would include negative infinity. This one would actually end up being a y is less than as well, again, because you'd flip the sign. So this one, you would get this 3, it would be less than, so it would include negative infinity, so that's why it's everything shaded over here. And it would also be shaded up here, but what's shaded in gray is what works for all three equations, which Desmos shows it a little bit differently. This one would be a y is greater than after you flip the sign, which is why it's shaded above the red. It would include positive infinity up here, right? But basically, all of the inequalities create this what's called a feasibility region, which is just an area of the graph where everything that's in here is a combination of x and y that works for all, like it works for all three, right? And where you're going to find the maximum and minimum values of this is always going to be at your corner points, right? So you only have 3 corner points. We have a triangle. So all that you would want to do is test out those 3 points. So just looking at the graph, right, we have a corner point, which is going to be um, right here, which we can say that that one looks like it's 2 comma 6. And again, if you did it on Desmos or on your graphing calculator, you can intersect and find it exactly. This one right here looks to be -1, -3. And this one over here looks like it's 6 comma 4. All right, so we have our 3 corner points that are all part of the inequality just because it was less than or equal to, so these are okay. And that's always going to be the case with these. So what we're going to do now is plug them back into our z equation, 3x plus 4y, right? And if we plug 3x plus 4y in with these points for x and y, we're going to find out like, the output 3x plus 4y, if I plug those in there, I think it gives me 30, right? 3 times 2 plus 4 times 6 is 30. 3 times -1 plus 4 times -3 gives me -15. And 3 times 6 plus 4 times 4 would give me 34. Right, so the maximum of this is -15. I'm sorry, the minimum of this is -15. The maximum is 34. The 30, I mean, we had to find it, but it's not part of the answer, right? The two answers for the minimum is -15, the maximum is 34. That's it, right? We don't even worry about the coordinate points in the final answer. It's just the actual values for the z equation. Right, so here's an on your own problem. Here's the z equation, here's your constraints. I would try and do it on Desmos, so you can pause the video and try and get your answers there, and then resume it when you're done. And if you've done that, I have, that's what I have on Desmos, right? So I put the 3 in, the inequalities, if you didn't find it, it's just right here if you click on the keypad. So, I'm less than the red one, so I'm over here. The blue one, I'm going to be less than when you flip the sign, so I'm over here. And the green one is going to be greater than when you flip the sign, so I'm up here. So this triangle here is my feasibility region. So I have -0.909, 2.273, 2, -5, and -6, -13. So those are your 3 corner points. So when you plug them into these equations, right? I did that on my graphing calculator, and I get 8.67 or 638. That's going to be my maximum. It's the only positive number that I have out of these 3, right? Ignore the top one, that's different. And then obviously the minimum is going to be -63.4. The -19 is something in between, so I don't take it. So again, maximum, minimum, and if you had those, good. The only other really thing that we could have is like, let's say for this inequality, you can only plug in values of x that are greater than 0. For this one, you can only plug in y's that are greater than 0. For this one, only less than 5. So these are like constraints on top of constraints. When you do that, it seems like it's going to be like an impossible question. But if you graph these all separately, it will always work out. So the first step is literally, I mean, first step, it says probably get all of these y equals. If you have Desmos, you don't have to worry about it, so don't worry about it. But then graph each one almost separately and then just kind of see where they are. So you don't have to do that now. I don't want to take up too much time. But like when you do, right, if you had a graphing calculator, I would just say your window should start at x equals 0 and end at x equals 5. Start with y equals 0 for the minimum. And then you're kind of like your whole screen. You're like, you don't worry about this stuff over here because it doesn't exist. Because it's hard to graph vertical lines on your graphing calculator. Desmos does it though, and we have a graph right here. So right here we have like, we have 1, 2, 3, 4, 5, 6 corner points. And you can do the intersection on Desmos. Graphing calculator, you just do the value button, and then you could figure out x equals 0, and then you just hit the up arrow to get to the next line. But you got your corner points there. I'm not going to read them all off. You can kind of see them. And then you would plug it into the z equation, which I think I gave it to you. Yep, -0.4x, 3.2y, and then you'd get these outputs. So again, your maximum would be 18.8 and your minimum would be -2, right? That would take a lot longer just because there's so many constraints, but you could still do it, right? So last thing really to do, and then a quick note at the end, you can pause it, do this on Desmos. Again, just graph these all separately and see if you can find the max and min of 2x minus 2y. And if you've done that, right, that should be this one, which we graphed all here. So this is a lot of stuff going on. If you kind of look at the inequalities, I think we have this feasibility region here. So we have 1, 2, 3, 4, 5 different points, right? So what you would want to do is plot these points, put them into 2x minus 2y, and then see what you get for values. So these are your 5 points if you want to be able to get an idea of what they are. I did those, right? Most of these are kind of easy, right? When you plug in 3, 2, you get an output of 2. When you plug in 3, 5, you get an output of -4. When you plug in 0, 4, you get an output of -8. -8 is actually going to be your minimum. 0, 2.5 is -5. This one here is the only one with decimals, so I did that on my calculator, which is up here. -1.2, not as big a minimum as -8 though. So it looks like the maximum is when you had 3, 2, you got a maximum of 2. So 2 would actually be the maximum. Again, not the point, the value of 2 is the maximum. So if you had that, good. It is possible. It might happen on one of the homework or one of the questions that you're going to do after this, where if you have an unbounded region, right? This feasibility region is bounded. It's what we've been doing all the whole lesson. If it's unbounded, right? Like this goes on and on and on forever. So there could be a chance that the maximum is infinity, right? Or it could be a chance if the minimum's infinity. Or it could be a chance that both are, and this actually has nothing to do with it. So you'd have to like try some points in the feasibility region and see if they're getting bigger or smaller. But you can have a maximum of infinity or negative infinity depending on if the region's unbounded. And that's it, right? I have some practice here. You don't have to do them. I think if you can do the worksheet stuff, then you'll be okay. Thanks, guys.